Good morning. In this lecture, we'll discuss about some properties on total orthonormal sets. A total set in a non-linear space X is a subset M whose span is dense in X. So accordingly, an orthonormal set in an inner product space X, which is total in X, is called a total orthonormal set or sequence or family respectively in X. So you can say that in brief, M is total if and only if the closure of a span of AM is equal to be the full space X. Or you can say that a non-empty subset M of an inner product space X is said to be total if and only if the vector X belongs to be X is orthogonal to all the vectors in M is a null vector only. And further, so let X be an inner product space, then an orthonormal set M in X said to be complete if M is a maximal orthonormal set in X, that is, if there does not exist any orthonormal set in X such that M is a subset of N. So the first result we will discuss, let X be an inner product space and M is a subset of AX, then if M is total in X, then X is perpendicular to be M, implies X is equal to be 0. Second one is if X is complete, then M is a total in X. So we'll discuss the first proof. So let H be a completion of the inner product space X, then X regarded as a subspace of H is dense in X, dense in H. So by the assumption M is a total in X, so span of AM is a dense in X, and hence it will be dense in H. So it follows that the orthogonal complement of AM in H is a null set by the definition. And second, we have to give that if X is complete, then M is a total in X. So we already said that M is complete by the definition in inner product if M is a maximal orthonormal set in X. So if X is a Hilbert space and the orthogonal complement of M is a null set, then M is a total in X. That is, for any subset M, non-empty subset of a Hilbert space H, the span of M is dense in M, if and only if the orthogonal complement of is equal to be null set. So we get the result. So next is any dense subset of an inner product space is a complete. So let A be a dense subset of an inner product space X. So there exists a sequence of elements Xn in A such that Xn converges to be X belongs to be X. So let X perpendicular to be A. So now the inner product of X comma Xn converges to be inner product of X comma X, and by definition this is equal to be norm of Ax. But here we have considered up that this Xn is an A, and we said that X is perpendicular to be A. So but we have inner product of X comma Xn is equal to be 0 for all n. So it means that this norm of Ax square is equal to be 0. Hence X is equal to be 0, that is A is total by the definition. The next one is an orthonormal set in an inner product space. X is complete if and only if X is perpendicular to be A, then X is equal to be 0 in X. So let A be an orthonormal set in X which is complete, and assume that this X belongs to be X such that X is perpendicular to be A, where X is non-zero, and let Y is equal to be X by norm of Ax. So if we consider the norm over this Y, this is equal to be norm of Ax over norm of X, which is equal to be 1. So norm of Y is equal to be 1. Then A union this Y is an orthonormal set in X contains A properly, and which is a contradiction to the fact that A is complete. So we can say that our assumption here is that x is non-zero is not true. So we have x is equal to be 0. So conversely, let x is perpendicular to be A. So x is equal to be 0. We assume this. So now we have to prove that A is complete. So now we suppose that A is not complete. So then there exists an orthonormal set B in AX such that A is a subset of a B. If X belongs to be a B minus A, then X belongs to be B and X does not belongs to be A. So as X belongs to be B, so norm of AX is equal to be 1, so which implies that the X is not equal to be 0, which is a contradiction. So A is a maximal orthonormal set and hence A is complete. So thus we have said that the orthonormal set A for X in an inner product space is complete if and only if it is total in X. So now give us we discuss some of the example. Let X is the L2 space and define the inner product in X by the inner product of X y is equal to the summation of a xi I eta I bar, where X is equal to be xi1 xi2 and so on, and y is equal to be eta 1 eta 2 so on belongs to be a L2 space. So let A is equal to be a orthonormal set in X where these EIs is equal to be having a 0, 0 and so on 1, and this 1 will be in the ith place only, and 0 and so on. So we get the E1 having the 1 in the first place, E2 having 1 in the second place and so on. So let X belongs to be X such that the norm of X is equal to be 1 and X is perpendicular to be A. So the inner product of X comma EI is equal to be 0. So now the set X and the union A is the orthonormal set and A is a subset of this collection X, E1, E2, so on. So we can say that the X can be written as a summation of a xi I, eta, EI. So we have a inner product of X comma EI is equal to be xi I, which implies that xi I is equal to be 0 for all I. So we can say that X is equal to be 0, 0, 0 and so on, having a 0 elements. So hence A is incomplete. So now we discuss the Parseval's equality. So which tell us that an orthonormal set M in a Hilbert space H is total if and only if the summation of a modulus of a x comma ek, the inner product of x comma ek square is equal to be norm of a x square for all x belongs to be M. So now if M is not total, then there is a non-zero element x in a which is perpendicular to be M in H. And since x is perpendicular to M, we have a 0 on the left hand side of a Parseval's equality. So whereas the right hand side, which is equal to be norm of x square, is not equal to be 0. Hence, if Parseval's equality holds for all x belongs to be H, then M must be total in H by the. So conversely, assume that M to be total in H. So consider any x belongs to be H and its non-zero Fourier coefficients arranged in a sequence, that is inner product of x comma e1, x comma e2 and so on, and define y as a summation of the inner product of x comma ek into ek. Now first we have to show that this x minus y is perpendicular to M. So for every ei occurring in a y is equal to be a summation of inner product of x comma ek into ek. Using the orthonormality we have inner product of x minus y comma ei is equal to be the inner product of x comma ei minus of summation of inner product of x comma ek into the inner product of ek ei. So which is equal to be the inner product of x comma ei minus inner product of x comma ei, because we know that we're using up the definition of a Kronecker delta. So now for every v belongs to be M, not in a y, which is equal to be a summation of inner product of x comma ek ek, we have inner product of x comma v is equal to be 0. So that the inner product of x minus y comma v is equal to be the inner product of x comma v minus summation of inner product of x comma ek into inner product of ek comma v, which is equal to be 0 minus of 0, which is equal to 0. So it follows that the x minus y is perpendicular, this belongs to be m perpendicular. Since m is a total, so we have the orthogonal complement of m is equal to be null set, is equal to be 0. Hence x minus y is equal to be 0. It implies that x is equal to be y. So therefore we have the norm of x square, which is equal to be inner product of summation of x comma ek into ek, and summation of x comma em is equal to be summation of k into the inner product of x comma ek into the or complement of x comma ek, which is equal to be norm of x, and hence the result. Thank you.